Hello everyone. In the last video lecture, we learned about the three major designs of bioreactors. That is the stirred tank bioreactors, bubble column bioreactors, and air-lift bioreactors. So here, these three are not the all. Okay, there are other types of bioreactors, and here we will learn about those other types, such as packed bed bioreactors, fluidized bed bioreactors, trickle bed bioreactors. So first we'll start with packed bed bioreactors. Okay, so in this kind of bioreactors, that is packed bed bioreactors, immobilized or particulate biocatalysts are used. Immobilized means, this biocatalyst cannot move. Immobilized, mobilization has been prevented. Okay, so basically this is called, I think you know the word immobilization. When we immobilize a biocatalyst, what we do, we attach the biocatalyst with something. Okay, we attach the biocatalyst, say for example we can attach the biocatalyst to a to some particles. Okay, so for that reason they will not be able to move. Okay, so they will be in fixed position. The biocatalyst will be in fixed position in this type of bioreactors. Okay, so anyway, the packed bed bioreactors are used with immobilized or particulate biocatalyst. For example, during the production of aspartate and fumarate. Okay, what happens? Conversion of penicillin to 6-amino penicillinic penicillinic acid and resolution of amino acid isomers. These are also done in the fermentation, and in this case, packed bed bioreactors are used. Okay, and in this kind of bioreactors, damage due to the particle attrition is minimal. Okay, compared with stirred bioreactors, because in stirred bioreactors mechanical stirrer are used which can damage the particles. Okay, in this kind of bioreactors there are some problems actually. Although there is some benefits, but there are also some problems. Okay, so for example, mass transfer can be sometimes problematic here. Anyway, this can be overcome. Mass transfer between the liquid media and the solid catalyst is, in this kind of bioreactors, packed bed bioreactors, mass transfer between the liquid medium and the solid catalyst is facilitated at high liquid flow rate through the bed. Okay, in the stirred tank bioreactors, the catalyst and the medium, they are in continuous mixing process, so mass transfer is easier. But in this case, the catalysts are fixed; they cannot move. Yet, we can achieve the required mass transfer at by using high liquid flow rate through the bed. Okay, and to achieve this, packed are often operated with liquid recycle. So what does it mean? So this one. Okay, this is an schematic figure of packed bed bioreactors. The catalysts are packed here, that is immobilized here. So for example, the liquid, that means the media, we can inject it through here. You can supply the media through here using a pump. So the liquid, if we use high force, the velocity of the media moving upwards will be high. So in that time, the mass transfer can occur between the liquids and the catalyst. Okay, and what happened, like suppose you pumped the media through here, the media will travel, that is go upward, and then again you can recycle it. Again you can pump it here. Okay, so by this way we can increase the mass transfer. Okay, anyway, the kettle is prevented from leaving the columns by screens at the liquid exit. You can say that, okay, we are pumping the liquid from here, it will create a force. So, this force, because of this force, the biocatalyst, although they are immobilized, they can leave here, right? Escape from here, but usually they are prevented. We can just use a screen here, okay? We can put something which will prevent the movement of the catalyst, okay? Okay, anyway, this was about the mass transfer, but how we achieve the addition in case of this packed bed bioreactors. Okay, why addition is necessary? because cells need oxygen, or biocatalysts need oxygen for their work. Okay. Anyway, I mean, in case of stirred tank bioreactors, we just directly, directly insert the, insert the oxygen or air into the bioreactors. But in case of packed bed bioreactors, we actually cannot do that, and we cannot directly asperge the air into the packed bed bioreactors because they can create some problems. For example, bubble coalescence can occur. Okay, and bubble coalescence will produce gas pockets in the in the immobilized catalyst. Okay, so if gas pockets are formed, okay, so mass transfer will be hampered. In addition, channeling or misdistribution also can occur if we directly asperge the air into the bioreactor. Okay, so what are the problems if we directly introduce the air into the bioreactors? Uh, Flow channeling or misdistribution, and also formation, bubble coalescence, okay, which will produce gas pockets, and gas pockets will hamper the mass transfer. Okay, if the mass transfer is hampered, the growth of the cells, if we use cells for, in this kind of bioreactors, the growth of the cells will be hampered. Okay. Anyway, the packed beds, they are unsuitable for processes which produce large quantities of carbon dioxide or other gases, which can become trapped in the packing. Okay, basically, if a large amount of carbon dioxide or other gases are produced, they'll also produce gas pockets. Okay, so that's why, these packed bed bioreactors, they are not suitable for those processes, in which processes large quantities of carbon dioxide and other gases are produced. Okay, so this was about the packed bed bioreactors. Then another one, fluidized bed bioreactors. Okay, so we just learned that packed bed bioreactors have some disadvantages. So we can overcome these advantages by using fluidized based bioreactors. Why fluidized based bioreactors have some advantages over packed bed bioreactors? Because in fluidized based bioreactors, particles are in constant motion. So that's why channeling and clogging of the bed are avoided. Okay, and also in addition, air can be introduced directly into the column. In case of packed bed, we cannot introduce air directly into the column. Instead, in packed bed, we have to do that in another vessel. Okay, in another vessel, we do the introduction of air into the media. Okay, then we transfer that media or inject that media into the column. But in case of fluidized bed bioreactor, we can directly introduce the air into the column. Okay, and fluidized bed bioreactors are used in wastewater treatment with sand or similar material supporting mixed microbial populations, and with flocculating organisms in brewing and production of vinegar. Okay, if you look at this figure, this right side one, this is an cartoon figure of fluidized based bioreactor. Okay, so like in the fluidized bed bioreactors, the catalyst, they can move. Okay, they can continuously move. Okay, so you can directly introduce the air into here. Okay, so this was fluidized bed. Then another type, the trickle bed. Okay, trickle bed bioreactors. It is a variation of the packed bed bioreactors. Okay, so it's almost similar like the packed bed, but there is a variation. What kind of variation? In this type of bioreactors, the liquid, that means the media, is sprayed onto top of the packing and trickles down through the bed in a small rivulets. Okay, and air may be introduced at the base because the liquid phase is not continuous throughout the column. Air and other gases move with relative ease around the packing. Okay, and trickle beds bioreactors are used widely for aerobic wastewater treatment. aerobic wastewater treatment. Okay, so in this figure, this one is the trickle bed bioreactor. So basic design is almost same. I mean, in case of packed bed, the biocatalysts, they are immobilized in immobilized form. Also, in case of the trickle bed reactors, catalyst, they are immobilized. Okay, and what is the difference? In case of a packed bed, the medium is pumped from the bottom to but in case of uh, trickle bed, the media, they are sprayed on top of the bioreactor. So when after the media is sprayed, they trickle through this biocatalyst, okay, and finally get out from the pump column. Okay, okay. Similar with the packed bed, you can again recycle this liquid. Okay, I mean that means you can again pump the same liquid into the into the column. Okay, and it actually has an benefit over the packed bed. But I mean, in case of packed bed, we cannot directly introduce the air, pump the air into the column. Okay, but in case of trickle bed bioreactors, you can directly introduce the air into the column. Okay. Okay, these were some other types of bioreactors, and this figure, okay, you can ignore this figure. These are some more colorful figure. Okay, basically the same. Okay, so we're done with the bioreactors type. Now we'll talk about some other parts of the bioreactors. First, asperger. You already know what is the function of asperger. Okay, asperger is used to introduce the gas into the air. Okay, so in STR, that means stricter bioreactors, air is added to the culture medium under pressure by a asperger. Okay, and asperger, they usually contain a ring with many small holes or a tube with a single orifice. The design of asperger can be different, like the porous asperger type. Okay, the porous asperger, they form a smaller bubbles, orifice asperger type or nozzle asperger type. Okay, so which asperger we have to use depend on the process. I mean, what kind of media we are using. The media is more concentrated or less concentrated. What kind of agitation system we are using. That means what kind of agitator or stirrer we are using. What kind of cells we are using. Okay. Okay, then agitators. Again, you already know what agitators do. Okay, agitators are used like the impellers. Okay, they're part of the agitators. Agitators are used to do the mixing. That means agitators are used for thorough dispersion of the gas within the bioreactor. Okay, and to achieve this one, usually a mechanical agitator are used. Okay, and okay, the mixing is not the sole purpose of the mechanical agitator. They do another important task. What task? I mean, the impellers of the agitators, they breaks larger bubbles into smaller ones, disperses the bubbles throughout the medium, and enhance the residence time of the bubbles in the reactor. So I mean, when we introduce air into the media through asperger, bubbles are formed. Okay, so if the size of the bubbles are bigger, mass transfer, that means especially the mass transfer will be less. So if we can break the size of the bubbles, there will be a smaller bubbles, right? So we know a smaller bubbles has more surface area than the larger bubbles. So as if you can produce a smaller bubbles, the surface area will increase and mass transfer will be more efficient. Okay, and we can do this by using impellers because impellers can break larger bubbles into smaller ones. Okay. Anyway, efficient gas dispersion depends on several factors like the size of the holes in the asperger, the type of impeller and its rotational speed, I mean, the design of impeller can vary greatly. Actually, there are several different types of, several different design of impellers. Okay, and different design of impellers, they, their functionality. Okay, the mechanism of their work is different. Okay, and the physiochemical properties of the liquid phase. Okay, so in this, particularly in this lecture, I didn't added the different design of impeller, but however, in the box, I will add a different PPT, okay, different PowerPoint slide. There, you can find the different designs of the impeller. So if you are interested, I'll suggest you to also read that one. Okay, that file will be named like extra reading materials. Okay, well. Some more parts of the bioreactor. Cooling jacket. So what can be the purpose of cooling jacket? It will cool down the bioreactor. So why cooling is necessary? When the fermentation will be on, lots of heat will be produced because of the physiological activity of the because of the metabolism by the cells, right? When the fermentation process will be on, and lots of chemical reactions, biochemical reactions will be going on inside there. It will produce lots of heat, and high temperature, they affect the cells. Okay, they affect the cells. They affect the physiological state of the cells, and if the physiological state of the cells are affected, yield will be decreased. We will get less product. Okay, so it's important that we'll control the heat of the bioreactor. We have to keep the temperature of the bioreactor within the range. Okay, so for do that, we need to use some kind of cooling system. Okay, one thing can be done, right? We can directly use cooling coil. If you put some cooling coil inside the fermenter, okay, which are also called internal coils, they can they could easily cool down the media. But using of cooling coils have a problem. If we use internal cooling coils, uh, these cooling coils can get coated by microorganisms, okay, which will prevents the cooling and interfere with the proper agitation of the product. So that's why, instead of, although internal cooling coils are better, instead of internal cooling coils, cooling jacket are used. Okay, this jacket, they wrap the fermenter, and if you flow cold water through this cooling jacket, okay, they will eventually absorb the temperature from the inside of the fermenter and control, by this way, control the temperature. Okay, foaming control. Okay, foam is a problem. Okay, especially when when you use high level of agitation, more foaming, more foam will be produced. Okay, and excessive foam, they can create various problems, such as the excessive foam can wet the filter at the port through which the introduced air exits the bioreactor. From the bottom, we introduced air. Okay, and it need to be exited. Okay, and after we inject the air from the bottom, it travel through the liquid media, do all its work, and then it exits the bioreactor. And for this for their this exits, there are some port in the bioreactor. Okay, and this port contains some filter. Okay, so if excessive foam are produced, this foam can wet the filter. Okay, so if the filter is wet, I mean the exit of the airflow will be hampered. That means the airflow exit will be decreased. Okay, and it will increase the chance of contamination. Okay, to control the foam, there are anti-foaming agents. So anti-foaming agents can be used, or mechanical foam breakers can be used. Okay. Anti-foaming agents are widely used. However, the anti-foaming agents, they're chemical. So this chemical can cause some troubles in the fermentation process, such as the chemical agents. That means the chemical antifoams. They can hamper microbial growth by preventing oxygen transfer, inhibiting cellular enzymes. It can contaminate the final product. Okay. And however, foaming can also be controlled by providing sufficient head space, I mean empty space at the top of the bioreactor. Okay, and usually working volume of culture is only about 75% of the total volume of the bioreactor. That means 25% head space, 25% empty space. Theoretically, if you can, I mean, increase this space, okay, you can control, I mean, you can more efficiently control the foam. But you know there is a problem. You just cannot keep 50% of the bioreactor empty. Okay, it will increase the operating cost. Okay, so we have to design the process in a way that, I mean, we have to keep the optimal head space. Okay. Okay, so this was about some parts of the bioreactors. Now again, and to talk about the talk about some advantages of bubble column bioreactors and air-lift bioreactors over stick tank bioreactors. Okay, bubble columns and air-lift bioreactors, they have some advantages over STRs, such as these are more energy efficient than STRs. Because in case of STR, mechanical stirrer are used, and mechanical stirrer, they need energy. Also, the bubble column and air-lift bioreactors, the shear force is low. Okay, so if the shear force is low shear force is more comfortable for the cells that are used as biocatalyst in the bioreactors. Okay, so now why low shear force is better? So why it is important that we should reduce the shear forces? Okay, because genetically engineered microorganisms are more susceptible to lysis when exposed to shear stress than are unmodified organisms, because the extra metabolic burden of synthesizing a foreign protein often causes genetically engineered microorganisms to form weakened cell walls. Actually, we use various genetically modified microorganisms nowadays. So, for example, insulin is produced by genetically modified organisms. Also, many antibiotics are produced by genetically engineered organisms. That means many commodities, okay, many commercially important products are produced by genetically engineered microorganisms. And these genetically engineered microorganisms, they are more susceptible to lysis by shear forces. Okay, so if we have to use genetically engineered microorganisms, it better to lower the shear forces. Okay, actually we must have to lower the shear forces. Okay, and then a frequent cellular response to the shear forces decrease synthesis of all cellular proteins, including the recombinant protein. Okay, and shear stress can alter the physical and chemical properties of the cells, so that the downstream processing steps become more difficult to perform. Okay, so that's all for this lecture. I mean, that's all for this part of this lecture. In the next part, I'll talk about some process by which we can solve some problems of solve some when we use genetically engineered microorganisms, we have to, there are some challenges. Okay, like for example, one challenges is these engineered microorganisms are more susceptible to shear forces. So there are some additional challenges. So in the next part, I'll talk about some of the challenges, and also we'll talk about how those challenges can be resolved. Okay, so thank you.